Hello fellow scientists. Today my plan is to extract manganese metal from normal standard AA batteries. Now the way I plan to do this is by a very exothermic displacement reaction known as a thermite reaction. The materials that I plan to use are manganese dioxide from the cathode of the AA batteries and aluminium powder, which I shall make from aluminium foil. The batteries are old dead AA batteries that I found around the house, as there is no longer a local recycling plant for them due to their nature of causing fires in said recycling plants. They closed them all down, so I thought, why not, let's have some fun chemistry experiments with them rather than let them go to waste in landfill or have to drive a long way to recycle them elsewhere. Now the first step in extracting the manganese dioxide from the batteries is to get into the wee buggers. This is a lot easier said than done, as the metal casing is very firmly held together. It's almost as if they don't really want people to get inside. However, with enough persuasion and a strong grip with a pair of pliers, it is possible to get your way in. Now, there are two main types of AA batteries. There is the carbon zinc battery, and then there is the alkaline battery. I've shown two extended footage films of me extracting the manganese dioxide from here, which is a zinc carbon battery, and next will be the alkaline battery. The main difference between a zinc carbon battery and an alkaline battery is the makeup. Now, in a zinc carbon battery, we have a zinc casing with a manganese dioxide cathode inside and a carbon rod running through the centre. The way to extract the manganese dioxide is to simply just peel back the outer zinc casing and extract the manganese dioxide and carbon rod from inside. The flaw with this plan is that it's very hard not to snap the carbon rod with the tools I have, which is simply a pair of pliers. The pair of pliers tends to apply a bit too much stress onto the carbon rod, which causes it to snap rather than be pulled out. However, if paired with a rotating motion, it does allow for the rod to be removed. There is also a kind of a paper layer separating the manganese dioxide cathode from the zinc outer casing. This is so the actual battery function can work. It acts as like a solid electrolyte, and I would assume that this paper is soaked in a sort of, actual electrolyte. This is why it should be a good idea to wear gloves during the whole of this experiment. I tended to not bother during the zinc carbon battery extractions, although this is very bad scientific practice. It's simply because at this point in time I didn't actually have any gloves. However, when it came to dismantling the alkaline batteries, I did wear some nitrile gloves because I didn't really fancy the idea of incredibly caustic potassium hydroxide electrolyte getting on my fingers and burning me. Now, as you can see, to extract the fine powder from inside the casing, I'm using a pair of tweezers, but any other kind of tool will suffice. I'd say that a metal spatula or a glass steroid or something would do the job just as well, if not better. I'm only using a pair of needle nose pliers, as it's not pliers. Forgive me, I'm incredibly tired. Tweezers, I said that already. Anyway, I'm using the tweezers to pull it out just because that's what I had on hand. A fun part about this whole experiment extraction is that every part of the battery is useful. The outer casing is a supply of zinc. The carbon rod can be used for electrolysis or arc creation with a high voltage, and the manganese is used in this experiment. Here we move on to the alkaline battery. Now, the actual physical structure of an alkaline battery is a bit different. Again, I mentioned how it's chemically a bit different, well, I will in a second, but it's physically a little bit different in the fact that it doesn't have a lip for pliers to peel back to allow it to be peeled. So a saw, a junior hacksaw, has to be used to open up an alkaline battery. The actual chemical structure is different in the sense that the manganese dioxide cathode is incredibly contaminated with carbon. Well, it's not contaminated because for the battery it is designed to be that way, but for our purposes it is contaminated, and this will impact the reaction, as it will severely limit how much actual manganese dioxide comes into contact with aluminium powder in the thermite. Now, how the alkaline battery works is that there is a very fine zinc powder in the centre rather than a carbon rod, and this zinc powder is separated from the manganese by a permeable membrane, which is generally kind of like a wrapped paper. Now, this is soaked in potassium hydroxide, which acts as the electrolyte and allows the electrons to flow through and complete a circuit when the top and bottom are connected in whatever appliance uses the AA battery. The outer casing in this case obviously isn't zinc, it's often just stainless steel. Well, not even stainless steel, just steel. And this, because as you can see, the manganese dioxide comes into direct contact with the casing, so this proves that it can't be the zinc, otherwise there'd be kind of reactions going on there. A thing we can see with the carbon contaminated manganese dioxide is that it's a lot stiffer. It kind of forms a lattice, kind of very hard structure. It doesn't want to lose that shape even after it's removed from the battery. This is in sharp contrast to the slightly purer, I'd say, manganese dioxide from the zinc carbon battery that was just a powder, and the second that you took it out of the battery it was a powder. It had no kind of strength holding it into any shape. A A thing to bear in mind with the structure of the alkaline battery is that there is a small metal rod through the centre, which is a current collector. It's generally made of brass, and that just massively increases the connection between the zinc powder and the bottom terminal, allowing it to work as functionally as it does. Here I use the tweezers to kind of use the battery's own strength against it. I can pull out a chunk, and we can see here that it definitely wants to maintain that shape. It's a very solid, firm structure. In future runs, I found that an easier way to do it, a lot more faster way anyway, is to simply hold the battery in a vice while it is sawed, and this crushes the very hard manganese dioxide into a more of a powder, which makes extraction a lot more easier. But here we can clearly see that the tube of manganese dioxide carbon mixture is incredibly firm and doesn't want to lose its structure. Even when we pull out the zinc powder centre, it holds on to a kind of ring shape. Now, I was curious to explore this, the anode part, and we can see that it is definitely a powder. We can see it's kind of grey, so we would assume heavy metal. And we know that it is in fact zinc powder with potassium hydroxide acting as an electrolyte. Here's just a time lapse of a couple of batteries that I took apart and extracted more manganese dioxide from. I think in total I took apart about 12 of each sort of battery. Here is the crude yield of manganese dioxide from just the alkaline batteries. The next step, of course, is to make powdered aluminium, and to do this I decided to grind up aluminium foil that I found as kitchen foil, which was very cheap at Tesco's. This is a very useful and available source which I think everyone can have access to. I decided to use a coffee grinder that I purchased from Argos for £15, and this is another very accessible way of creating basically an inexhaustible supply of aluminium powder. Now the powder formed here could be a lot finer, and that could be achieved by using a ball mill, which more accurately mimics the kind of attritional process that happens in kind of rivers and the ocean. Now here, most of the breakdown into fine powder happens because of aluminium balls kind of that have been formed by the circular motion hitting into each other and knocking them down, breaking into very small fragments, which in turn hit other fragments and break them down. So if I was to be incredibly patient and have all the time in the world just to hold down the grind button, it would in fact leave an incredibly fine powder. However, a ball mill kind of would automate this process and make it a lot more user friendly. It would also mitigate the risk of exposure to aluminium powder that has had a direct correlation with increased risk of Alzheimer's, which is quite an undesirable thing, which is why during this process I wore a respirator, and eye protection. I should have also worn gloves, however this was filmed at a time that I didn't have access to the gloves. I hope I haven't killed it. Now that we've ground up all our aluminium powder, what we can do is weigh it so we have an accurate reading on an idea of how much aluminium we have, as I estimated this would be the limiting reagent in our reaction. This was because I didn't have very much aluminium powder aluminium foil available for me to use. So I knew that this was going to be the limiting reactant. Now I use my hand here to prevent lots of clouds of aluminium powder to get into the air, as this could settle over all of my equipment and just cause problems to people nearby. And as you can see, the incredibly fine powder settled on my fingers, on my hand, to make them shiny. This was definitely a problem, and I washed it off straight away, as exposure could lead to heavy metal poisoning or, as I said, increased risk of Alzheimer's in later life. The particle size varies an awful lot, from incredibly fine to quite large, visible size. Now, I thought this should be okay, as the energetics of the thermite reaction is quite extreme, and so a large particle size should, in theory, limit how energetic the reaction will be, which would make it more handleable, more controllable. Now that we've extracted both of our reactants, it is time to do a bit of equation work. the easy way to balance equations is just to write out the molecular formulas of all of the reactants and products, and then simply work out the molar ratios by using the conservation of, well, just the law of conservation, I suppose, isn't it? Nothing's created or destroyed, so the same amount of atoms must be present in the reactant and product side of a reaction. Next, I noted down the molecular masses of the compounds, which I worked out from the atomic masses of each of the atoms present. The equation I'm using, the mass is equal to the molecular mass times the mole, is a very useful equation which allows us to find the links between the mass of the substance, the molecular mass of its compound, and the moles that it takes up in the equation. Firstly, at the top is the molar ratio. However, this isn't accurate to this reaction, as that would involve there being a specific amount. There would be 4 moles worth of aluminium powder, which I didn't have. We can work out I had 2.15 moles of aluminium powder, and so from there we can work out what ratio of my manganese dioxide we're going to have to use to keep a stoichiometric balance between both reactants. See, it wouldn't really matter if the ratio was much off because of the high carbon contamination. I didn't consider this into my equation, and this probably was the reason for my drastically low yield at the end, which, albeit some spoilers, however, it is expected. So, having worked out how many grams of the manganese dioxide I will need, I weighed it out using the set of scales. Now, although I worked it out to 2 decimal places, my scales are only accurate to, well, not even to 1 decimal place, so any hope of accuracy is already out the window. This makes it a bit easier to accept the losses that are made during transit of one vessel to another, which is made very obvious in a second when the manganese dioxide on the paper here is poured into the aluminium powder. Then you can see a black smudge left behind on the paper, which represents a very small loss of manganese dioxide. However, as the scales are inaccurate and a high carbon contamination, there isn't really much of a concern about this. However, this is obviously not quantitative transfer, and it should try to be remedied in a real chemical circumstance. Now, to break down the quite large particle size at the moment of the manganese dioxide, I decided to bring out the trusty coffee grinder again. This should not only break down the large particle size, but also mix the 2 compounds together in a very intimate mixture, which should help to increase the rate of reaction. By having the particles both small and close together, it increases the likelihood of well, using particle theory, increases likelihood of successful collisions between the particles forming a reaction. Now, as this looks definitely like a very fine powder, and pouring it was, well, it was another example of poor quantitative transfer of the powder. I think a funnel definitely would have improved the transfer rate, although at this point in time my funnel was buried from a different experiment that I had been doing, and I was unable to use it. Although at this point a loss shouldn't really matter, as I have quite a lot of reactant and they are mixed hopefully intimately in the correct ratio, so a loss would just limit the amount of product formed rather than cause a unstoichiometric balance between the two reactants, which could cause a different reaction to occur, or at least a different reaction to be favoured, possibly. So now that we have the thermite mix outside, it's time to work on how to light it. I decided to do this using a couple of sparklers, which are just rods of metal covered in magnesium powder with a strip of magnesium wrapped around them. I thought this would work best as magnesium burns at incredibly high temperatures, which would maximise the chance of it lighting. Now, the actual thermite reaction was, I wouldn't say very successful. Now, this is obviously due to the high carbon contamination, which would mean that there is incredibly low amounts of actual manganese dioxide, as this is the alkaline battery mix that I used. As you can see, there is a very small amount of thermite reaction occurring. It kicked up a lot of powder, and I was able to extract a couple of beads of manganese metal from the surface, once it had cooled down, obviously. Although most of this white powder is not aluminium oxide, it's just magnesium oxide. So this was my yield of manganese. It is incredibly small and very contaminated, but it is present. In future, I hope to purify up the manganese metal as well as finish off the rest of the unreacted reactants, which I hope to also purify to achieve this. Thank you ever so much for watching, everybody. It really means a lot to me. I know the commentary hasn't exactly been top notch, but I've had some awful trouble editing this video, and I've ended up having to re-record it. I think this is the third time now, so hopefully it'll work out. But thank you everybody so much for watching. It really means a lot to me, and hopefully I'll see you in the next video. Bye.